Hello everyone, it's Khurshid Ayub here. I welcome you to this lecture series which is on computational chemistry, concepts, theory, and applications. Let me give you a brief overview of this course, what will be covered here. So here's a list of the topics that I will try to cover in this course, starting from the potential energy surface, which is a fundamental of computational chemistry, then moving on to minima and saddle points. Then I will talk about thermodynamics and normal mode analysis. Then I will give you a brief overview of Schrödinger equation and quantum mechanics. Then moving on to molecular Hamiltonian and Born-Oppenheimer approximation. Then I will give you an overview of Hartree-Fock method. Then we'll discuss post-Hartree-Fock methods and why we are going to talk about post-Hartree-Fock method, and the reason lies behind in static and dynamic correlation. Then we'll move on to density functional theory, followed by basis function and basis set. Then we will talk about excited state calculations. We will also talk about restricted and open shell system. Then I will give you an overview of cost and accuracy. The cost here means computational cost, the time taken here. Then we will have a look on the strategies to reduce the computational cost. And then we will move on to molecular mechanics and force field, then semi-empirical methods, molecular dynamics, and Monte Carlo calculations. And finally, I will give you an overview of the properties calculation that can be done with computational chemistry. Now, having heard the name of computational chemistry, the question arises what the computational chemistry is. You will come across many different definitions. This is, in principle, the application of mathematical models and simulations to chemical problems using computers. Or in other words, it's a branch of chemistry that uses computer simulations and mathematical modeling to understand and predict the properties of chemical systems. This approach provides insight into complex molecular interactions and facilitates the design of new molecules or materials. The question arises, what can be done with computational chemistry? Now, before going into the list here, I want to tell you that the properties can be categorized into two different categories, like molecular or the bulk properties. I mean the properties which are associated with molecules or the properties which are the characteristic of bulk. Now, giving you an overview of a few properties that can be done in the category of molecular properties through computational tools. Again, this list is not exhaustive. You can calculate molecular energies, and with these energies, you can discuss reaction energies, barriers. We can also talk about the molecular geometries, the most stable geometry one, or even we can talk about local or global minima, conformational analysis, etc. We can also talk about electronic distributions, which will help us in understanding the reactivities. We can also talk about spectroscopic properties, for example, UV visible spectroscopy, IR and Raman spectrum, NMR spectrum, etc. With molecular dynamics, we can talk about reaction rates and mechanism. We can talk about protein folding. We can study polarizability, dipole moments. We can talk about quantitative structure-activity relationships. All of these properties are molecular properties. On the other hand, we can do some computational chemistry on bulk properties such as density, viscosity, hardness, melting point, etc. But there are some limitations of computational chemistry where we cannot calculate certain properties, such as if we are trying to solve rate equations, it's not possible with computational chemistry. Similarly, deconvolution of spectra is also not possible with computational chemistry. Again, this list is not exhaustive. There are many other things which are not yet possible with computational chemistry. Now, there may be a number of different softwares which can be used in computational chemistry, and the number of softwares are so much that it's not possible to list them all here. So what I have done here, I have jotted down a few prominent softwares. For example, for quantum mechanical calculations, the Gaussian software can be used, Vienna ab initio simulation package, which is commonly known as WASP. Similarly, CASTEP can also be used, Quantum Espresso, and Chem. Among these software, Gaussian is a popular software for molecular calculations, whereas periodic or bulk calculations can be done with WASP, Quantum Espresso, CASTEP, etc. For visualization of structures, we can use VMD, GaussView, PyMol, ChemCraft. These are the software which actually do not do any calculation, but they help in drawing the structure or visualizing the structures after calculation. For example, GaussView and Gaussian, they are complementary to each other. They are from the same incorporation like Gaussian incorporation. In GaussView, you can draw the structure, and then there's an interface which sends calculation to Gaussian software. Calculations are done by Gaussian software, and once the calculations are finished, the files can be opened back in GaussView. Similarly, VMD, PyMol, or ChemCraft are the other software which can be used for visualization. Similarly, another category of calculation is molecular modeling. For molecular modeling, the most common software is molecular operating environment. So now here I will give you a brief classification in computational chemistry. The classification can be of different types. For example, if you talk about systems, as mentioned previously in the section of properties, your system can be either small molecule or bulk. So I mean, one classification is based on system under consideration. It can be a molecular system or it can be a bulk system. When you talk about classification of methods in computational chemistry, or in other words, based on theory involved, the methods can be categorized into these 5 most common categories. The first one is force field or molecular mechanics, which is based on ball and spring approach, or in other words, it is called as classical mechanics. In this case, atoms are treated as balls, and the bond between them is treated as a spring. Now you can see in ball and spring approach, there is no electronic structure. So these methods, they ignore the electronic structure. Because of this simplification, these methods are much faster, but they have problem with the accuracy. So these calculations can be applied to those systems where quantum mechanical calculation can practically fail. For example, if you talk about large protein molecules, DNAs, RNAs, so these molecules are large enough that your quantum mechanical calculation will not work, so you are only limited with force field methods. Another class is ab initio methods. The word ab initio is actually a Latin word which means that from beginning. So it means in this case, the structure of the system is solved from quantum mechanical calculations without any empirical data. So it is full quantum mechanical treatment of electronic wave function that gives ab initio methods. Similarly, you can have semi-empirical methods. These are also called as semi-empirical molecular orbital methods. They are combination of ab initio methods and some parameterization either from experiment or from some higher method. So ab initio methods with an approximate or parameterized Hamiltonian leads to semi-empirical method. So if you are finding these terminologies a bit complicated, don't worry, these are going to come later in this course. But for the time being, you can get an idea that force field, molecular mechanics, or classical mechanics is a method which ignores electronic structure. It's based on ball and spring approach. The second category is ab initio methods, which is based on full quantum mechanical treatment of electronic wave function. The third class is semi-empirical. Empirical means coming from experiment. Semi-empirical means something is coming from experiment and something is coming from calculation. So in this case, it's a mix of ab initio method with an approximate or parameterized Hamiltonian. So what is Hamiltonian? It's going to come later when we are going to discuss the Hartree-Fock method. The fourth category is density functional theory methods. It's a fully quantum mechanical treatment of electron density. Now the difference between ab initio and density functional is in ab initio, there's electronic wave function which is used for calculation, but in the density functional theory method, it's again quantum mechanical treatment, but on electron density. The fifth class here is molecular dynamics. The word dynamic clearly tells you that it is something movement, related to movement. So in this approach, molecules are allowed to move, and in this case, it follows spatiotemporal evolution of a chemical system, or in other words, how a system look like if it is seen in the time frame of. So molecules are free to move under certain condition, and how the structure of the system evolves as a result of this movement, that is known as spatiotemporal evolution of a chemical system. Another classification is based on properties. Now, in terms of properties, there are two main categories of method. The first one is energy calculation methods. These methods relate the energy of a molecule to its geometry, and that is the fundamental of all calculations. In other words, in computational chemistry, the first thing that you're going to do is relate the energy to its structure. That is very much fundamental to all calculations in computational chemistry. And this relationship between structure and energy is used to construct the potential energy surface. Now again, to construct potential energy surface, you have different approaches available, and these are the four approaches that we have discussed on the last slide. It is force field or molecular mechanics, ab initio methods, semi-empirical molecular orbital methods, and density functional theory methods. The second one is property calculation method. They evaluate specific properties of a system, and they use the information from energy calculation methods, and these include geometry optimization as well as molecular dynamics. For geometry optimization, it determines structure and energies of reactant, products, and transition state. And from these information or from these energies, it can give us an idea about reaction energies, either energy of reaction or energy of activation. Energy of reaction is the energy of product minus energy of reactant, whereas energy of activation is energy of transition state minus energy of reactant. As far as the molecular dynamics is concerned, I mentioned previously that it is following spatiotemporal evolution of a chemical system. So in this case, we see how the coordinates of a system change after a certain time. For example, if you're looking at a system from time plus delta t, it will depend on initial position. This part here, Ri bracket t plus delta t, is going to give you position at certain time. But this part here is going to give you the position at the start. Now it's going to take contribution from velocity and also going to take contribution from acceleration. And based on velocity and acceleration, it's going to determine what will be the final position of the system. In properties calculation, we can also evaluate the specific property of a system. It uses information from energy calculation methods, and this can include statistical mechanical treatment, which we are going to see when we talk about thermodynamic properties. And we can also talk about normal mode analysis in the harmonic approximation. When we talk about normal mode analysis, it means we are talking about the vibrational spectrum of a system. It gives vibrational frequencies. It can be giving you IR, Raman spectra. And we know that in IR or Raman spectroscopy, the main parameter is force constant, which is actually the second derivative of energy with respect to displacement. So the vibrational frequency depends on force constant and reduced mass through relationship given here. 1 over 2 pi square root k over mu.